Learning objectives. In this chapter, the user would learn the following in detail: definition and properties of Z transform, rational Z transforms, inverse Z transform, one-sided Z transform, analysis of LTE systems in Z domain, analysis of linear time invariant systems in the Z domain. Main goals: characterize response to inputs, characterize system properties, stability, causality, etc. in Z domain. Response of systems with rational system functions. X of Z tends to, H of Z tends to, Y of Z. Goal: characterize Y of n. Assume H of Z is a pole zero system, that is H of Z equal to B of Z divided by A of Z. Input signal as a rational Z transform of the form X of Z equal to N of Z divided by Q of Z. Then Y of Z equal to H of Z into X of Z equal to B of Z into N of Z divided by A of Z into Q of Z. So, the output signal also has a rational Z transform. How do we find Y of n? Since Y of Z is rational, we use PFE, is called partial fraction expansion, to find Y of n. Y of Z equal to summation k equal to 1 to n ak divided by 1 minus pk into z power minus 1 plus summation k equal to 1 to z qk divided by 1 minus qk into z power minus 1. Assume poles of system P1 etc. Pn are unique. Poles of input signal Q1 etc. QL are unique. Poles of system and input signal are all different. Zeros of system and input signal differ from all poles. So, no pole zero cancellation. Proper form: causal input sequence and a causal LTA system. Then, Y of n equal to summation k equal to 1 to n or k into pk power n into u of n is natural plus summation k equal to 1 to l sk into qk power n into u of n is forced. The output signal for a causal pole zero system with input signal having rational Z transform is a weighted combination of geometric progression signals. If there are repeated poles, then of course the PFE has terms of the form n into p power n into u of n etc. The output signal has two parts. The pk terms are the natural response ynr of n of the system. The input signal affects only the residues rk. Each term of the form pk power n into u of n is called a mode of the system. The qk terms are the forced response yfr of n of the system. The system affects only the residues sk. Response of pole zero systems with non-zero initial conditions. The input signal x of n is causal. To determine the output y of n for n greater than or equal to 0, we use the one-sided Z transform. One side Z transform becomes y plus of z equal to minus summation k equal to 1 to n ak into z power minus k into within the bracket y plus of z plus summation n equal to 1 to k y of minus n into z power n plus summation k equal to 0 to m bk into z power minus k into x plus of z. Since x of n is causal, set x plus of z equal to x of z, y plus of z equal to summation k equal to 0 to m bk into z power minus k divided by 1 plus summation k equal to 1 to n ak into z power minus k into x of z minus summation k equal to 1 to n ak into z power minus k into summation n equal to 1 to k y of minus n into z power n divided by 1 plus summation k equal to 1 to n ak into z power minus k equal to h of z into x of z plus n naught of z divided by of z, where n naught of z equal to minus summation k equal to 1 to n ak into z power minus k into summation n equal to 1 to k y of minus n into z power n. The output of the system with non-zero initial conditions can be subdivided into two parts: zero state response of the system, zero input response of the system. Zero state response of the system defined in the z domain as yn of z equal to h of z into x of z. Zero input response of the system defined in the z domain as yn plus of z equal to n naught of z divided by a of z. Total response is the sum of these two components, which can be expressed in the time domain by determine the inverse z transforms of y zs of z and y zi plus of z separately. Then add the results. Thus, y of n equal to y zs of n plus y zi of n. Since the denominator of y zi plus of z is a of z, its poles are p1, p2, etc. pn. Zero input response as the form y zi of n equal to summation k equal to 1 to n dk into pk whole power n into u of n. Total response of the system y of n equal to summation k equal to 1 to n ak dash pk whole power n into u of n plus summation k equal to 1 to l qk into qk power n into u of n, where by definition ak dash equal to ak plus dk. This development indicates that the effect of the initial conditions is to alter the natural response of the system through modification of the scale factors ak. No new poles introduced by non-zero initial conditions. No effect on the forced response of the system. Transient and steady state response. The response of a system to a given input can be separated into two components: the natural response and the forced response. The natural response of a causal system has the form ynr of n equal to summation k equal to 1 to n ak into pk whole power n into u of n. If all the poles have magnitude less than unity, then this response decays to 0 as n underscore infinity. In such cases, we also call the natural response the transient response. Smaller magnitude poles lead to faster signal decay, so the closer the pole is to the unit circle, the longer the transient response. The forced response has the form yfr of n equal to summation k equal to 1 to l capital Qk into small qk whole power n into u of n. If all of the input signal poles are within the unit circle, then the forced response will decay towards 0 as n underscore infinity. If the unit signal has a pole on the unit circle, then there is a persistent sinusoidal component of the input signal. The forced response to such a sinusoid is also a persistent sinusoid. In this case, the forced response is also called the steady state response. Example: determine the transient and steady state responses of the system characterized by the difference equation y of n equal to 0.5 into y of n minus 1 plus x of n, where the input signal is x of n equal to 10 into cos pi n divided by 4 into u of n. The system is initially at rest, that is, it is relaxed. Solution. The system function for the system is h of z equal to 1 divided by 1 minus 0.5 into z power minus 1. And therefore, the system as a pole at z equal to 0.5, the z transform of the input signal x of z equal to 10 into 1 minus 1 divided by root 2 into z power minus 1, the whole divided by 1 minus root 2 into z power minus 1 plus z power minus 2. Consequently, y of z equal to h of z into x of z equal to 10 into 1 minus 1 by root 2 into z power minus 1 divided by 1 minus 0.5 into z power minus 1 into 1 minus e power jpi divided by 4 into z power minus 1 into u into 1 minus e power minus jpi divided by 4 into z power minus 1 equal to 6.3 divided by 1 minus 0.5 into z power minus 1, the 6.78 into e power minus j 28.7 divided by 1 minus e power jpi divided by 4 into z power minus 1 plus 6.78 into e power j 28.7 divided by 1 minus e power minus jpi divided by 4 into z power minus 1. The natural or transient responses YNR of n equal to 6.3 into 0.5 whole power n into u of n, and the forced or steady state responses YFR of n equal to 6.78 into e power minus j 28.7 into e power j pi I n divided by 4 plus 6.78 e power j 28.7 into e power minus j pi I n divided by 4 into u of n equal to 13.56 into cos of pi by 4 n minus 28.7 into u of n. The steady state persists for all n greater than or equal to 0, just as the input signal persists for all n greater than or equal to 0. Causality and stability. A causal linear time invariant system is one whose unit sample response h of n satisfies the condition h of n equal to 0 where n less than 0. A linear time invariant system is causal if and only if the region of convergence of the system function is the exterior of a circle of radius r less than infinity, including the point z equal to infinity. The stability of the LTI system can be expressed in terms of the characteristics of the system function. A necessary and sufficient condition for a LTI system to be BIBO stable is summation n equal to minus infinity to plus infinity modulus of h of n less than infinity. The condition implies that h of z must contain the unit circle within its region of convergence, since h of z equal to summation n equal to minus infinity to plus infinity h of n into z power minus n. It follows that modulus of h of z less than or equal to summation n equal to minus infinity to plus infinity modulus of h of n into z power minus n equal to summation n equal to minus infinity to plus infinity modulus of h of n into modulus of z power minus n. When evaluated on the unit circle, that is modulus of z equal to 1, modulus of h of z less than or equal to summation n equal to minus infinity to plus infinity, modulus of h of n. If the system is BI/BO stable, the unit circle is contained in the region of convergence of h of z. The converse is also true. A linear time invariant system is BI/BO stable if and only if the region of convergence of the system function includes the unit circle. A causal system is characterized by a system function h of z having region of convergence the exterior of some circle radius r. A causal linear time invariant system is BI/BO stable if and only if all the poles of h of z are inside the unit circle. Pole zero cancellations. When a z transform has a pole that is at the same location as a zero, the pole is cancelled by the zero and consequently the term containing that pole in the inverse z transform vanishes. Pole zero cancellations can occur either in the system function itself or in the product of the system function with the z transform of the input signal. By properly selecting the position of the zeros of the input signal, it is possible to suppress one or more systems modes, pole factors in the response of the system. By proper selection of the position of the zeros of the system function, it is possible to suppress one or more systems modes of the input signal from the response of the system. When the zero is located very near the pole but not exactly at the same location, the term in the response has very small amplitude. Non-exact pole zero cancellation can occur in practice as a result if insufficient numerical precision used in the representing the coefficients of the system. Multiple order poles instability. A necessary and sufficient condition for a causal linear time invariant system to be BI/BO stable is that all its poles lie inside the unit circle. The input signal is bounded if its Z transform contains poles Qk, k equal to 1, 2, etc. L, which satisfies the condition modulus of Qk less than or equal to 1 for all k. Forced response of the system is also bounded even when the input signal contains one or more distinct poles on the unit circle. YFR of n equal to summation k equal to 1 to L capital Qk into small qk whole power n into u of n. BI/BO stability requires system poles be strictly inside the unit circle. Multiple order poles result in an output sequence ak into n power b into pk whole power n into u of n, where 0 less than or equal to b less than or equal to m minus 1 and m is the order of the pole. No bounded input signal can produce an unbounded output signal if the system poles are all inside the unit circle. Systems containing poles on the unit circle are the digital oscillators. Such systems are called marginally stable. The Shurkin stability test. The poles of the system are the roots of the denominator polynomial of h of z, namely a of z equal to 1 plus a1 into z inverse plus a2 into z power minus 2 plus etc. plus an into z power minus n. When system is causal, all roots of a of z must lie inside the unit circle for the system to be stable. Computation procedures that aid in determining if any roots of a of z lie outside the unit circle are called stability criteria. We denote a polynomial of degree m by am of z equal to summation k equal to 0 to m am of k into z power minus k, where am of 0 equal to 1. The reciprocal or reverse polynomial bm of z of degree m is defined as bm of z equal to z power minus m am of z power minus 1 equal to summation k equal to 0 to m am of m minus k into z power minus k. In Skurkon stability test, to determine if the polynomial a of z has all roots inside the unit circle, we compute a set of coefficients called reflection coefficients k1, k2, etc. kn from the polynomials am of z. An of z equal to a of z, kn equal to an of n. Compute lower degree polynomials am of z, comma, m equal to n, n minus 1, n minus 2, etc. 1. According to recursive equation, am minus 1 of z equal to am of z minus km into bm of z divided by 1 minus km square, where the coefficients km are defined as km equal to am of m. The Skurkon stability test states that the polynomial a of z has all its roots inside the unit circle if and only if the coefficients km satisfy the condition modulus of km less than 1 for all m equal to 1, 2, etc. n. The Skurkon stability test can be programmed in a digital computer and very useful in terms of arithmetic operation. It requires only n square multiplications to determine the coefficients km, where m equal to 1, 2, etc. n. Following algorithm is equivalent to recursive equation am minus 1 of z equal to am of z minus km into bm of z divided by 1 minus km square. Set an of k equal to ak, where k equal to 1 to etc. n and kn equal to an of n. Then for m equal to n, n minus 1, etc. 1, compute km equal to am of m and am minus 1 of 0 equal to 1 and am minus 1 of k equal to am of k minus km into bm of k divided by 1 minus km square, where k equal to 1 to etc. m minus 1, where bm of k equal to am of m minus k, where k equal to 0, 1, 2, etc. m. Stability of second order systems. Consider a causal two-pole system described by the second order difference equation y of n equal to minus a1 into y of n minus 1 minus a2 into y of n minus 2 plus b0 into x of n. The system function is h of z equal to y of z divided by x of z equal to b0 divided by 1 plus a1 into z power minus 1 plus a2 into z power minus 1 equal to b0 into z square divided by z square plus a1 into z plus a2. The system has two zeros at the origin and poles at p1 into p2 equal to minus a1 by 2 plus or minus square root of a1 square minus 4a2 divided by 4. The system is BIBO stable if the poles lie inside the unit circle, that is, if modulus of p1 less than 1 and modulus of p2 less than 1. These conditions can be related to the values of the coefficient a1 and a2. In particular, the roots of a quadratic equation satisfy the relations a1 equal to minus of p1 plus p2, a2 equal to p1 into p2. a2 must satisfy the condition modulus of a2 equal to modulus of p1 p2 equal to modulus of p1 into modulus of p2 less than 1. a1 can be expressed as modulus of a1 less than 1 plus a2. From the recursive equations we get k1 equal to a1 divided by 1 plus a2 and k2 equal to a2. The system is stable if and only if modulus of k1 less than 1 and modulus of k2 less than 1. Consequently, minus a1 less than a2 less than 1, or modulus of a2 less than 1 minus 1 less than a1 divided by 1 plus a2 less than 1, or a1 less than 1 plus a2, a1 greater than minus 1 minus a2. The system is stable if and only if the point a1, a2 lies inside the triangle called the stability triangle. Behavior of the system can be obtained from the unit sample responses for below cases. Real and distinct poles a1 square equal to 4a2, real and equal poles a1 square equal to 4a2, complex conjugate poles a1 square less than 4a2, real and distinct poles a1 square equal to 4a2. Since p1, p2 are real and p1 not equal to p2, the system function can be expressed in the form h of z equal to a1 divided by 1 minus p1 into z power minus 1 plus a2 divided by 1 minus p2 into z power minus 1, where a1 equal to b0 into p1 divided by p1 minus p2 and a2 equal to minus b0 into p2 divided by p1 minus p2. Consequently, the unit sample responses h of n equal to b0 divided by p1 minus p2 into p1 power n plus 1 minus p2 power n plus 1 into u of n. Therefore, the unit sample response is the difference of two decaying exponential sequences. Real and equal poles a1 square equal to 4a2. In this case, p1 equal to p2 equal to p equal to minus a1 by 2. The system function is h of z equal to b0 divided by 1 minus p into z power minus 1 the whole square, and hence the unit sample response of the system is h of n equal to b0 of n plus 1 into p power n into u of n, where h of n is the product term sequence and real sequence and a real decaying exponential sequence. Complex conjugate poles a1 square less than 4a2. Since the poles are complex conjugate, the system function can be factored and expressed as h of z equal to a divided by 1 minus p into z power minus 1 plus a star divided by 1 minus p star into z power minus 1 equal to a divided by 1 minus r into e power j omega naught into z power minus 1 plus a star divided by 1 minus r into e power minus j omega naught into z inverse, where p equal to r into e power j omega and 0 less than omega naught less than pi. Note that when the poles are complex conjugates, the parameters a1 and a2 are related to r and omega naught according to a1 equal to minus 2r cos omega naught, a2 equal to r square. The constant a in the partial fraction expansion of h of z is easily shown to be a equal to b0 into p divided by p minus p star equal to b0 r into e power j omega naught divided by r into e power j omega naught minus e power minus j omega naught equal to b0 into e power j omega naught divided by j 2 sin omega naught. Consequently, the unit sample response of a system with complex conjugate poles is h of n equal to b0 into r power n divided by sin omega naught into e power j of n plus 1 omega naught minus e power minus j n plus 1 omega naught divided by 2j into u of n equal to b0 into r power n divided by sin omega naught into sin of n plus 1 into omega naught into u of n. In this case, h of n has an oscillatory behavior with an exponentially decaying envelope when r less than 1. The angle omega naught of the poles determines the frequency of oscillation, and the distance r of the poles from the origin determines the rate of decay. Definition and properties of Z transform. Z transform. In this section, we introduce the Z transform of a discrete time signal, investigate its convergence properties, and briefly discuss the inverse Z transform. The direct Z transform. The Z transform of a discrete time signal x of n is defined as the power series x of z equivalents to summation n equal to minus infinity to plus infinity x of n into z power minus n, where z is a complex variable. This relation is called the direct Z transform because it transforms the time domain signal x of n into complex plane representation x of z. Z transform of a signal x of n is denoted by x of z equal to z of modulus of x of n, whereas the relationship between x of n and x of z is indicated by x of n is related to x of z in the presence of z. The Z transform is an infinite power series. It exists only for those values of z for which the series converges. The region of convergence ROC of x of z is the set of all values for z which x of z attains a finite value. A discrete time signal x of n is uniquely determined by its Z transform and the region of convergence. Example, determine the Z transform of the signal x of n equal to minus alpha to the power n u of minus n minus 1 equal to 0 when n greater than or equal to 0 and minus alpha power n when n less than or equal to minus 1. Solution. The Z transform is defined as x of z equivalents to summation n equal to minus infinity to plus infinity x of n into z power minus n. From above definition, we have x of z equal to summation n equal to minus infinity to plus infinity minus alpha power n into z power minus n equal to minus summation L equal to 1 to infinity a power minus 1 into z whole power L, where L equal to minus n. Using the formula a plus a square plus a cube plus etc. equal to, after taking the a as common, we getting a into 1 plus a square plus etc. equal to a divided by 1 minus a when modulus of a less than 1 gives x of z equal to alpha power minus 1 into z divided by 1 minus alpha power minus 1 into z equal to 1 divided by 1 minus alpha into z power minus 1, provided that modulus of alpha minus 1 z less than 1 or modulus of z less than modulus of a. X of n equal to minus alpha power n u of minus n minus 1 is related to x of z equal to 1 divided by 1 minus alpha into z power minus 1, where ROC modulus of z less than modulus of alpha. The ROC is now the interior of the circle having radius modulus of alpha. Anti-casual signal x of n equal to minus alpha into u of n minus 1 is in figure A. Then the ROC of its Z transform is in figure B. The inverse Z transform. The procedure for transforming from the Z domain to the time domain is called the inverse Z transform. An inversion formula for obtaining x of n from x of z can be derived by using the Cauchy integral theorem, which is an important theorem in the theory of complex variables. Z transform is defined by x of z equal to summation k equal to minus infinity to plus infinity x of k into z power minus k. Multiply both sides by z power n minus 1 and integrate both sides over a closed contour within the ROC of x of z which encloses the origin. Closed integral x of z into z power n minus 1 into dz equal to summation k equal to minus infinity to plus infinity x of k into closed interval z power n minus 1 minus k into dz, where c denotes the closed contour in the ROC of x of z taken in a counterclockwise direction. Interchange the order of integration and summation on right hand side. Closed integral x of z into z power n minus 1 into dz equal to summation k equal to minus infinity to plus infinity x of k into closed integral z power n minus 1 minus k into dz. Now invoke the Cauchy integral theorem, which states that 1 divided by 2 pi j with closed integral z power n minus 1 minus k into dz equal to 1 when k equal to 1 and 0 when k not equal to n, where c is any contour that encloses the origin. Hence, the desired inversion formula is x of n equal to 1 divided by 2 pi j with closed integral x of z into z power n minus 1 into dz. Properties of Z transform. The Z transform is very powerful tool for the study of discrete time signals and a system. The power of this transform is a consequence of some very important properties of the transform. Linearity. If small x1 of n is related to capital X1 of z in the presence of z and small x2 of n is related to capital X2 of z in the presence of z, then small x of n equal to a1 into x1 of n plus a2 into x2 of n is related to capital X of z, which is equal to a1 into x1 of z plus a2 into x2 of z. For any constants a1 and a2, the Z transform of a linear combination of signals is the same linear combination of their Z transforms. The linearity property helps us find the Z transform of a signal by expressing the signal as a sum of elementary signals, for each of which the Z transform is already known. Time shifting. If small x of n is related to capital X of z in the presence of z, then small x of n minus k is related to z inverse into capital X of z in the presence of z. The ROC of z power k into capital X of z is the same as that of capital X of z except for z equal to 0 if k greater than 0 and z equal to infinity if k less than 0. Scaling in the z domain. If small x of n is related to capital X of z in the presence of z at the region of convergence R1 less than modulus of z less than R2, then a power n into small x of n is related to capital X of a inverse into z in the presence of z at the region of convergence modulus of a into R1 less than modulus of z less than modulus of a into R2. For any constant a, real or complex, from definition of Z transform, Z of a power n into x of n equal to summation n equal to minus infinity to plus infinity a power n into x power n into z power minus n equal to summation n equal to minus infinity to plus infinity x power n into a power minus 1 into z whole power minus n equal to capital X of a power minus 1 into z. Since The region of convergence of capital X of Z is R1 less than modulus of Z less than R2. The region of convergence of capital X of A power minus 1 into Z is R1 less than modulus of A power minus 1 less than R2. Then modulus of A into R1 less than modulus of Z less than modulus of A into R2. To better understand the meaning and implications of scaling property, we express A and Z in polar form as A equal to R naught into e power I omega naught, Z equal to R into e power j omega, and we introduce a new complex variable omega equal to a power minus 1 into Z. Thus, Z of x of n equal to capital X of Z and Z of a power n into x of n equal to capital X of omega. Omega equal to a power minus 1 into Z equal to 1 divided by R naught into R into e power j into omega minus omega naught. Time reversal. If small x of n is related to capital X of Z in the presence of Z, the region of convergence is R1 less than modulus of Z less than R2. Then small x of minus n is related to capital X of Z power minus 1 in the presence of Z. The region of convergence is 1 divided by R2 less than modulus of Z less than 1 divided by R1. From definition of Z transform, Z of x of minus n equal to summation n equal to minus infinity to plus infinity x of minus n into Z power minus n equal to summation L equal to minus infinity to plus infinity x of L into Z power minus 1 whole power minus 1 equal to capital X of Z power minus 1, where the change of variable L equal to minus n is made. The region of convergence of x of Z power minus 1 is R1 less than modulus of Z power minus 1 less than R2, or equivalently 1 divided by R2 less than modulus of Z less than 1 divided by R1. Region of convergence for x of n is the inverse of that for x of minus n. If Z0 belongs to the region of convergence of x of n, then 1 divided by Z0 is the region of convergence for x of minus n. Holding a signal is equivalent to replacing Z by Z power minus 1 in the Z transform formula. Reflection in the time domain corresponds to inversion in the Z domain. Differentiation in the Z domain. If small x of n is related to capital X of Z in the presence of Z, then n into small x of n is related to minus Z d capital X of Z divided by dz in the presence of Z. By differentiating both sides of Z transform definition, we have d capital X of Z divided by dz equal to summation n equal to minus infinity to plus infinity small x of n into minus n into Z power minus n minus 1 equal to minus Z power minus 1 summation n equal to minus infinity to plus infinity n into x of n into Z power minus n equal to minus Z power minus 1 into capital Z of n into x of n. Convolution of two sequences. If small x1 of n is related to capital X1 of Z in the presence of Z and small x2 of n is related to capital X2 of Z in the presence of Z, then x of n equal to x1 of n star x2 of n is related to capital X of Z, which is equal to capital X1 of Z into capital X2 of Z. The region of convergence of capital X of Z is at least the intersection of that for capital X1 of z and capital X2 of z. Proof. The convolution of x1 of n and x2 of n is defined as x of n equal to summation k equal to minus infinity to plus infinity x1 of k into x2 of n minus k. The z transform of x of n is capital X of z equal to summation n equal to minus infinity to plus infinity x of n into z power minus n equal to summation n equal to minus infinity to plus infinity within the bracket summation k equal to minus infinity to plus infinity x1 of k into x2 of n minus k. Outside the bracket we have to write z power minus n. Upon interchanging the order of the summations and applying the time shifting property, we obtain capital X of z equal to summation k equal to minus infinity to plus infinity x1 of k into summation n equal to minus infinity to plus infinity x2 of n minus k into z power minus n equal to capital X2 of z into summation k equal to minus infinity to plus infinity x1 of k into z power minus k equal to capital X2 of z into capital X1 of z. The convolution property converts the convolution of two signals time domain to multiplication of their transforms. Computation of the convolution of two signals using Z transform requires following steps. Compute the Z transform of the signals to be convolved. Capital X1 of Z equal to Z of X1 of n. Then capital X2 of Z equal to Z of X2 of n, where the time domain is the Z. Multiply the two Z transforms. Capital X of Z equal to capital X1 of Z into capital X2 of Z, where the domain is Z. Find the inverse Z transform of capital X of Z. X of n equal to Z inverse into capital X of Z, where the domain is converted to the time domain. Example. Compute the convolution x of n of the signals. X1 of n equal to 1, minus 2, 1. X2 of n equal to 1 when 0 less than or equal to n less than or equal to 5 and 0 elsewhere. Solution. From Z transform definition we have capital X1 of Z equal to 1 minus 2 into Z power minus 1 plus Z power minus 2. Capital X2 of Z equal to 1 plus Z power minus 1 plus Z power minus 2 plus Z power minus 3 plus Z power minus 4 plus Z power minus 5. Multiply capital X1 of Z and capital X2 of Z. Capital X of Z equal to capital X1 of Z into capital X2 of Z equal to 1 minus Z power minus 1 plus Z power minus 6 plus Z power minus 7. Hence, X of n equal to 1 minus 1 0 0 0 0 minus 1 1. Correlation of two sequences. If x1 of n is related to capital X1 of Z in the presence of Z and x2 of n is related to capital X2 of Z in the presence of Z, then or x1 x2 of L equal to summation n equal to minus infinity to plus infinity x1 of n into x2 of n minus L is equivalent to or x1 x2 of Z equal to capital X1 of Z into capital X2 of Z power minus 1. Proof. Or x1 x2 of L equal to x1 of L into x2 of minus L. Using the convolution and time reversal properties, we easily obtain or x1 x2 of Z equal to Z of x1 of L into Z of x2 of minus L equal to capital X1 of Z into capital X2 of Z power minus 1. The ROC of or x1 x2 of Z is the intersection of that for capital X1 of Z and capital X2 of Z power minus 1. In case of convolution, the cross correlation of two signals is done via polynomial multiplication and then inverse transforming the result. Percival's relation. If x1 of n and x2 of n are complex valued sequences, when summation n equal to minus infinity to plus infinity x1 of n into x2 star of n equal to 2 pi j closed integral capital X1 of v into capital X2 star of 1 divided by v star into v inverse into dv. Multiplication of two sequences. If x1 of n is related to capital X1 of z in the presence of z and x2 of n is related to capital X2 of z in the presence of z, then x of n equal to x1 of n into x2 of n in the presence of z, capital X of z equal to 1 divided by 2 pi j closed integral capital X1 of v into capital X2 of z by v into v inverse into dv, where C is a closed contour that encloses the origin and lies within the region of convergence common to both capital X1 of v and capital X2 of 1 divided by v. Proof. The Z transform of x3 of n is capital X of z equal to summation n equal to minus infinity to plus infinity x of n into z power minus n equal to summation n equal to minus infinity to plus infinity x1 of n into x2 of n into z power minus n. Substitute the inverse transform. X1 of n equal to 1 divided by 2 pi j closed integral capital X1 of v into v power n minus 1 into dv. For x1 of n in the z transform capital X of z and interchange the order of summation and integration. Capital X of z equal to 1 divided by 2 pi j closed integral capital X1 of v into within the bracket summation n equal to minus infinity to plus infinity x2 of n into z divided by v whole power minus n into v power minus 1 into dv. The sum in the brackets is the transform capital X2 of z evaluated at z by v. Therefore, below is the desired result. Capital X of z equal to 1 divided by 2 pi j closed integral capital X1 of v into capital X2 of z by v into v power minus 1 into dv. The initial value theorem. If x of n is casual, that is x of n equal to 0 for n less than 0, then x of 0 equal to limit z tends to infinity capital X of z. Proof. Since x of n is casual z transform, definition gives capital X of z equal to summation n equal to 0 to infinity x of n into z power minus n equal to x of 0 plus x of 1 into z power minus 1 plus x of 2 into z power minus 2 plus etc. Summary of Z transform properties. We can see in the table whatever we learned before in a simplest form. Inversion of the Z transform. The inverse Z transform is given by x of n equal to 1 divided by 2 pi j closed integral x of z into z power n minus 1 into dz, where the integral is a contour integral over a closed path C that encloses the origin and lies within the region of convergence of x of z. C can be taken as a circle in the region of convergence of x of z in the z plane. There are three methods used for evaluation of the inverse Z transform. Number 1. Direct evaluation by contour integration. Number 2. Expansion into a series of terms in the variables z and z power minus 1. Number 3. Partial function expansion and table lookup. The inverse Z transform by contour integration. The Cauchy residue theorem is used to determine the inverse Z transform directly from the contour integral. Cauchy residue theorem. Let f of z be a function of the complex variable z and c be a closed path in the z plane if the derivative df of z divided by dz exists on and inside the contour C, and if f of z has no poles at z equal to z0, then 1 divided by 2 pi j closed integral f of z divided by z minus z0 into dz equal to f of z0 if z0 is inside C and 0 if z0 is outside C. If k plus 1 order derivative of f of z exists and f of z has no poles at z equal to z0, then 1 divided by 2 pi j with the closed integral f of z divided by z minus z0 whole power k into dz equal to 1 divided by k minus 1 factorial into d power k minus 1 of f of z divided by dz power k minus 1 at z equal to z0 if z0 is inside C and 0 if z0 is outside C. The values on the right hand side of above equations are called the residues of the pole at z equal to z0. The results in above equations are two forms of the Cauchy residue theorem. If the integrand of the contour integral is p of z equal to f of z divided by g of z, where f of z has no poles inside the contour C and g of z is a polynomial with the distinct roots z1, z2, etc. zn inside C, then 1 divided by 2 pi j closed integral f of z divided by g of z into dz equal to 1 divided by 2 pi j closed integral summation I equal to 1 to n ai of z divided by z minus zi into dz equal to summation I equal to 1 to n 1 divided by 2 pi j closed integral ai of z divided by z minus zi into dz equal to summation I equal to 1 to n ai of zi, where ai of z equal to z minus zi into p of z equal to z minus zi into f of z divided by g of z. In the case of the inverse z transform, we have x of n equal to 1 divided by 2 pi j closed integral x of z into z power n minus 1 into dz equal to summation all the poles modulus of z inside C, residue of x of z into z power n minus 1 at z equal to zi equal to summation I z minus zi into x of z into z power n minus 1 at z equal to zi. The inverse z transform by power series expansion. Given a z transform x of z with its corresponding region of convergence, we can expand x of z into a power series of the form x of z equal to summation n equal to minus infinity to plus infinity cn into z power minus n, which converges to the given region of convergence. Then, by uniqueness of the z transform, x of n equal to cn for all n. When x of z is a rational, the expansion can be performed by long division. The method of long division will not provide answers for x of n when n is large because the long division becomes tedious. Although long division method provides a direct evaluation of x of n, a closed form solution is not possible except if the resulting pattern is enough to infer the general term x of n. Example: determine the inverse z transform of x of z equal to log of 1 plus a into z power minus 1, where modulus of z greater than modulus of a. Solution: using the power series expansion for log of 1 plus x with the modulus of x less than 1. X of z equal to summation n equal to 1 to infinity minus 1 whole power n plus 1 into a power n into z power minus n divided by n. Thus x of n equal to minus 1 whole power n plus 1 into a power n divided by n, where n greater than or equal to 0. Then 0 for n less than or equal to 0. Expansion of irrational functions into power series can be obtained from tables. The inverse Z transform by partial fraction expansion. In the table lookup method, we express the function x of z as a linear combination. X of z equal to alpha 1 into x1 of z plus alpha 2 into x2 of z plus etc. plus alpha k into xk of z, where x1 of z, etc., xk of z are expressions with inverse transforms x1 of n, etc., xk of n available in table of Z transform pairs. X of n, the inverse Z transform of x of z can be found using the linearity property as x of n equal to alpha 1 into x1 of n plus alpha 2 into x2 of n plus etc. plus alpha k into xk of n. If x of z is a rational function, we assume that a not equal to 1. X of z equal to n of z divided by d of z equal to b naught plus b1 into z power minus 1 plus etc. bm into z power minus m, the whole divided by 1 plus a1 into z power minus 1 plus etc. an into z power minus n. A rational function of above form is called proper if an not equal to 0 and m less than n. An improper rational function m greater than or equal to n can always be written as the sum of a polynomial and a proper rational function. An improper rational function m greater than or equal to n is expressed as x of z equal to n of z divided by d of z equal to c naught plus c1 into z power minus 1 plus etc. cm minus n into z power minus of m minus n plus n1 of z divided by d of z. Inversion of proper rational transforms. Let x of z be a proper rational function. X of z equal to n of z divided by d of z equal to b naught plus b1 z power minus 1 plus etc. plus bm into z power minus m, the whole divided by 1 plus a1 into z power minus 1 plus etc. plus an into z power minus n, where an not equal to 0 and m less than n. Multiply both numerator and denominator by z power n. X of z equal to b naught into z power n plus b1 into z power n minus 1 plus etc. bm into z power n minus m divided by z power n plus a1 into z power n minus 1 plus etc. plus an. The result contains only positive powers of z. Since n greater than m, the function is always proper. X of z divided by z equal to b naught into z power n minus 1 plus b1 into z power n minus 2 plus etc. plus bm z power n minus m minus 1 divided by z power n plus a1 into z power n minus 1 plus etc. plus an. To express above equations as a simple fractions, we factor the denominator polynomial into factors that contain the poles p1, p2, etc. pn of x of z. We distinguish two cases: distinct poles, multiple order poles. Distinct poles. Suppose the poles p1, p2, etc. pn are all different, distinct, then we seek expansion of the form x of z divided by z equal to a1 divided by z minus p1 plus a2 divided by z minus p2 plus etc. plus an divided by z minus pn. The coefficients a1, a2, etc. an can be determined by multiplying both sides of each of the terms z minus pk, where k equal to 1, 2, etc. n, and evaluating the resulting expressions at the corresponding pole positions p1, p2, etc. pn. Z minus pk into x of z divided by z equal to z minus pk into a1 divided by z minus p1 plus etc. plus ak plus etc. plus z minus pk into an divided by z minus pn. Consequently, with z equal to pk, ak equal to z minus pk into x of z divided by z at z equal to pk, where k equal to 1 to etc. n. Complex conjugate poles result in complex conjugate coefficients in the partial fraction expansion. Multiple order poles. If x of z has a pole of multiplicity L, that is, it contains in its denominator the factor z minus pk whole power L, then below expansion is no longer true. X of z divided by z equal to a1 divided by z minus p1 plus a2 divided by z minus p2 plus etc. plus an divided by z minus pn. The partial fraction expansion must contain the terms a1k divided by z minus pk, a2k divided by z minus pk the whole square plus etc. plus alk divided by z minus pk the whole power L. Consider x of z containing distinct poles. X of z equal to a1 into 1 divided by 1 minus p1 into z power minus 1 plus a2 into 1 divided by 1 minus p2 into z power minus 1 plus etc. plus an into 1 divided by 1 minus pn into z power minus 1. The inverse z transform x of n equal to z power minus 1 into x of z is obtained by inverting each term in above equation and taking the corresponding linear combination. Form the z transform pairs table. These terms can be inverted using the formula z inverse of 1 divided by 1 minus pk into z power minus 1 equal to pk whole power n into u of n if region of convergence modulus of z greater than modulus of pk. Causal signals and minus pk whole power n u of minus n minus 1 if the region of convergence modulus of z less than modulus of pk. Anti-causal signals. If the signal x of n is causal, the region of convergence is modulus of z greater than p maximum, where p maximum equal to maximum of modulus of p1, modulus of p2, etc. modulus of pn. X of n equal to within the bracket a1 into p1 power n plus a2 into p2 power n plus etc. plus an into pn power n into u of n. The contribution of two complex conjugate poles is of the form xk of n equal to within the bracket ak into pk power n plus ak star into pk star power n into u of n. Above two terms can be combined to form a real signal component. Let us express ak and pk in polar form, that is, amplitude and phase. ak equal to modulus of ak into e power j alpha, pk equal to rk into e power j beta. Substituting ak and pk in equation, xk of n equal to within the bracket ak into pk power n plus ak star into pk star power n into u of n. We get xk of n equal to modulus of ak rk power n into within the bracket e power j of beta 1n plus ak plus e power minus j beta 2n plus ak into u of n, or xk of n equal to 2 times of modulus of ak rk power n cos of within the bracket beta kn plus alpha k into u of n. Thus, z power minus 1 of ak divided by 1 minus pk into z minus 1 plus ak star divided by 1 minus pk star into z power minus 1 equal to 2 into modulus of ak r k power n cos of within bracket beta kn plus alpha k into u of n if the region of convergence is modulus of z greater than modulus of pk equal to rk. In case of multiple poles, either the real or complex, the inverse transform of terms of the form a divided by z minus pk whole power n is required. In case of double pole, the following transform pair is used. Z inverse of p into z power minus 1 divided by 1 minus p into z power minus 1 the whole square equal to n into p power n into u of n, provided that the region of convergence is modulus of z greater than modulus of p. Rational Z transforms. An important family of Z transforms are those for which x of z is a rational function, that is a ratio of two polynomials in z power minus 1 or z. Poles and zeros. The zeros of a Z transform, capital X of z are the values of z for which x of z equal to 0. The poles of a Z transform are the values of z for which x of z equal to infinity. If x of z is a rational function, then x of z equal to n of z divided by d of z equal to b naught plus b1 z power minus 1 plus etc. plus bm into z power minus m divided by a naught plus a1 z power minus 1 plus etc. plus an into z power minus n equal to summation k equal to 0 to m bk into z power minus k divided by summation k equal to 0 to n ak into z power minus k. If a naught not equal to 0 and b naught not equal to 0, we can avoid negative powers of z by factoring out the terms b naught into z power minus m and a naught into z power minus n as follows. Capital X of z equal to n of z divided by d of z equal to b naught into z power minus m divided by a naught into z power minus n into z power m plus b1 divided by b naught into z power m minus 1 plus etc. bm divided by b naught divided by z power n plus a1 divided by a naught into z power n minus 1 plus etc. plus an divided by a naught. Since n of z and d of z are polynomials in z, they can be expressed in factorized form as x of z equal to n of z divided by d of z equal to b naught by a naught into z power minus m plus n into z minus z1 into z minus z2 etc. z minus zm divided by z minus p1 into z minus p2 etc. z minus pn. X of z equal to g into z power n minus m into product k equal to 1 to m z minus zk divided by product k equal to 1 to n z minus pk, where g equivalent to b naught divided by a naught. Some common Z transform pairs are given. After reading the table, we can clearly understand Z transforms with region of convergence. Table. Some common Z transform pairs. Example. Determine the pole 0 plot for the signal x of n equal to a power n into u of n, where a greater than 0. Solution. From Z transform pairs table, x of z equal to 1 divided by 1 minus a into z power minus 1 equal to z divided by z minus a, where the region of convergence is modulus of z greater than a. X of z as 1 0 at z1 equal to 0 and 1 pole at p1 equal to a. Figure. Pole 0 plots for the casual exponential signal x of n equal to a power n into u of n. Pole p1 equal to a is not included in the region of convergence since the Z transform does not converge at a pole. Pole location and time domain behavior for casual signals. In this subsection, we consider the relation between the z-plane, location of a pole pair and the form, shape of the corresponding signal in the time domain. The characteristic behavior of casual signals depends in whether the poles of the transform are contained in the region modulus of z less than 1 or in the region modulus of z greater than 1 or on the circle modulus of z equal to 1. Since the circle modulus of z equal to 1 has a radius of 1, it is called the unit circle. If a real signal has a z transform with one pole has to be real. X of n equal to a power n into u of n is equivalent to capital X of z equal to 1 divided by 1 minus a into z power minus 1. Time domain behavior of a signal real pole casual signal as a function of the location of the pole with respect to the unit circle. The signal is decaying if the pole is inside the unit circle. Signal is fixed if the pole is on the unit circle. Signal is growing if the pole is outside the unit circle. A negative pole results in a signal that alternates in sign. A casual real signal with a double real pole has the form x of n equal to n into a power n into u of n. In contrast to the single pole signal, a double real pole on the unit circle results in an unbounded signal. Time domain behavior of casual signals corresponding to a double m equal to 2 real pole as a function of the pole location. The distance r of the poles from the origin determines the envelope of the sinusoidal signal and the angle with the real positive axis its relative frequency. Amplitude of the signal is growing if r greater than 1. Amplitude of the signal is constant if r equal to 1. Sinusoidal signals. Amplitude of the signal is decaying if r less than 1. A pair of complex conjugate poles corresponds to casual signals with oscillatory behavior. Casual real signal with simple real poles or simple complex conjugate pairs of poles, which are inside or on the unit circle are always bounded in amplitude. A signal with a pole near the origin decays more rapidly than one associated with a pole near the unit circle. If a pole of a system is outside the unit circle, the impulse response of the system becomes unbounded and consequently the system is unstable. The system function of a linear time invariant system. The convolution property expresses the relationship in the z domain as y of z equal to h of z into x of z, where y of z is the z transform of the output sequence y of n, x of z is the z transform of the input sequence x of n, h of z is the z transform of the unit sample response h of n. H of z equal to y of z divided by x of z. Since h of z equal to summation n equal to minus infinity to plus infinity h of n into z power minus n. H of z represents the z domain characterization of a system. H of n is the corresponding time domain characterization of the system. H of z and h of n are equivalent descriptions of a system in the two domains. The transform h of z is called the system function, describing the system by a linear constant coefficient difference equation. Y of n equal to minus summation k equal to 1 to n ak into y of n minus k plus summation k equal to 0 to m bk into x of n minus k. The system function can be determined by computing the z transform of both sides by applying time shifting property of the difference equation. We obtain y of z equal to minus summation k equal to 1 to n ak into y of z into z power minus k plus summation k equal to 0 to m bk into x of z into z power minus k. Then y of z into 1 plus summation k equal to 1 to n ak into z power minus k equal to x of z into summation k equal to 0 to m bk into z power minus k. Just cross multiplying, we get y of z divided by x of z equal to summation k equal to 0 to m bk into z power minus k divided by 1 plus summation k equal to 1 to n ak into z power minus k, or equivalently h of z equal to summation k equal to 0 to m bk into z power minus k divided by 1 plus summation k equal to 1 to n ak into z power minus k. Therefore, a LTI system described by a constant coefficient difference equation as a rational system function. If ak equal to 0 for 1 less than or equal to k less than or equal to n, h of z equal to summation k equal to 0 to m bk into z power minus k equal to 1 divided by z power m into summation k equal to 0 to m bk into z power m minus k. The system containing only trivial poles at z equal to 0 and m non-trivial zeros is called an all-zero system. Such a system has finite duration impulse response FIR and is called an FIR system or moving average system. If bk equal to 0 for 1 less than or equal to k less than or equal to m, h of z equal to b naught divided by 1 plus summation k equal to 1 to n ak into z power minus k equal to b naught into z power n divided by summation k equal to 0 to n ak into z power n minus k, where a naught equivalent to 1. The system function containing both poles and zeros with n poles and m zeros is called a pole zero system. Due to the presence of poles, a pole zero system is an IIR system. One-sided Z transform. Definition and properties. The one-sided or unilateral Z transform of a signal x of n is defined by x star of z equal to summation k equal to 0 to infinity x of n into z power minus n. The one-sided Z transform differs from the two-sided transform in the lower limit of summation, which is always 0, whether or not the signal x of n is 0 for n less than 0. Due to this choice of lower limit, the one-sided Z transform has the following characteristics. It does not contain information about the signal x of n for negative values of time, that is, for n less than 0. It is unique only for casual signals because only their signals are 0 for n less than 0. The one-sided Z transform x plus z of x of n is identical to the two-sided Z transform of the signal x of n into u of n. Since x of n into u of n is causal, the region of convergence of x plus z is always the exterior of a circle. Thus, when we deal the one-sided Z transform, it is not necessary to refer to the region of convergence. Properties of one-sided Z transform. Shifting property. Case 1. Time delay. X of n is related to capital X plus of z. Then x of n minus k is related to z power minus k of capital X plus of z plus summation n equal to 1 to k x of minus n into z power n, where k greater than 0. In case x of n is causal, then x of n minus k is related to z power minus k capital X plus of z. Proof. From one-sided Z transform definition, x plus of z is equivalent to summation n equal to 0 to infinity x of n into z power minus n. We have z plus x of n minus k equal to z power minus k into within the bracket summation L equal to minus k to minus 1 x of L into z power minus L plus summation L equal to 0 to infinity x of L into z power minus L equal to z power minus k into within the bracket summation L equal to 0 to minus k x of L into z power minus L plus x plus of z. Changing the index from L to n equal to minus L, the result is obtained. The meaning of the shifting property can be intuitively explained if we write x of n minus k is related to z power minus k into within the bracket capital X plus of z plus summation n equal to 1 to k x of minus n into z power n, where k greater than 0, as z plus of x of n minus k equal to x of minus k plus x of minus k plus 1 into z power minus 1 plus etc. plus x of minus 1 into z power minus k plus 1 plus z power minus k x plus of z, where k greater than 0. Case 2. Time advance. If x of n is related to capital X plus of z in the presence of z plus, then x of n plus k is related to z power k into within the bracket capital X plus of z plus summation n equal to 0 to k minus 1 x of n into z power minus n, where k greater than 0. Proof. From one-sided z transform definition, capital X plus of z equal to summation n equal to 0 to infinity x of n into z power minus n. We have z plus of x of n plus k equal to summation n equal to 0 to infinity x of n plus k into z power minus n equal to z power k into summation L equal to 0 to infinity x of L into z power minus L, where we have changed the index of summation from n to L equal to n plus k. Now, from we obtain x plus of z equal to summation L equal to 0 to infinity x of L into z power minus 1 equal to summation L equal to 0 to k minus 1 x of L into z power minus 1 plus summation L equal to k to infinity x of L into z power minus 1. Final value theorem. If x of n is related to capital X plus of z in the presence of z plus, then limit n tends to infinity x of n equal to limit z tends to 1 z minus 1 into capital X plus of z. If the region of convergence of z minus 1 into x plus of z includes the unit circle. Solution of difference equations. The one-sided z transform is a very efficient tool for the solution of difference equations with non-zero initial conditions. It achieves that by reducing the difference equation relation, the two domain signals to an equivalent algebraic equation relating their one-sided z transforms. The signal in the time domain is obtained by inverting the resulting z transform. Example. Determine a closed form expression for the nth term of the Fibonacci sequence. Solution. Let y of n be the nth term of the Fibonacci sequence. Y of n satisfies the difference equation y of n equal to y of n minus 1 plus y of n minus 2. With the initial conditions y of 0 equal to y of minus 1 plus y of minus 2 equal to 1. Then y of 1 equal to y of 0 plus y of minus 1 equal to 1. From y of 1 equal to y of 0 plus y of minus 1 equal to 1, we have y of minus 1 equal to 0. Then y of 0 equal to y of minus 1 plus y of minus 2 equal to 1 gives y of minus 2 equal to 1. Thus, we have to determine y of n greater than or equal to 0 with initial condition y of minus 1 equal to 0 and y of minus 2 equal to 1 by taking one-sided property and using shifting property. We get y plus of z equal to z inverse into y plus of z plus y of minus 1 plus z power minus 2 into y plus of z plus y of minus 2 plus y of minus 1 into z power minus 1, or y plus of z equal to 1 divided by 1 plus z power minus 1 minus z power minus 2 equal to z square divided by z square minus z minus 1. We can invert y plus of z by partial fraction expansion method. The poles of y plus of z are p1 equal to 1 plus root 5 divided by 2, p2 equal to 1 minus root 5 divided by 2, and corresponding coefficients are a1 equal to p1 root 5 and a2 equal to p2 root 5. Therefore, y of n equal to 1 plus root 5 divided by 2 root 5 into 1 plus root 5 divided by 2 whole power n minus 1 minus root 5 divided by 2 root 5 into 1 minus root 5 divided by 2 whole power n into u of n, or y of n equal to 1 divided by root 5 into 1 by 2 whole power n plus 1 into within the bracket 1 plus root 5 whole power n plus 1 minus 1 minus root 5 whole power n plus 1 into u of n. Conclusion. In this chapter, we have covered the following in detail: definition and properties of Z transform, rational Z transforms, inverse Z transform, one-sided Z transform, analysis of LTE systems in Z domain.